All right, so let's think about how that would play out on some of the systems that we've been thinking about. Let's think about how it might play out, let's say, for a pendulum. So here's my pendulum, okay? Here's my stable fixed point. Here's the region. I do a LQR stabilization, some local stabilization. So I've got some controller that can stabilize this region. And this is an idea that many of you, I could see it seeded in your head back when we were talking about these things initially, right? We've got a local linear controller here. Why not try to fill the space with other local linear controllers, right? Okay, so the problem is that the simple recipe is just have a lot of controllers which individually stabilize the system, right? And then I'll put them together and one will dump into each other. Think about the places where you can possibly stabilize the pendulum, right? So I can only stabilize points, and even if I have no torque limits, I can stabilize points with velocity 0, right? So I could stabilize sort of any of these points along the theta equals 0 axis. I can't actually stabilize a point up here, right? So I can't have a funnel that lives just up here because the system's going to leave, right? I mean, I can't have a funnel that lives. I could have funnels along here until I run out of torque, and I can't stabilize this if I don't have enough torque to hold myself there. Okay, so there's something more that has to happen. The other big tool that we have, right, is trajectory optimization, right? So it's easy to find a trajectory that gets me from the downright to the upright if I just do trajectory optimization. So the big question here is, can we put those ideas together, okay, and try to make something that will have this Kodacek, and actually, it's funny about the idea of funnels is so sort of pervasive and strong that nobody takes credit for it. So Dan will credit Matt Mason, and Matt Mason will credit Mike Erdman, and I haven't actually asked Mike Erdman, but someone credited Mark Rabert, and he doesn't seem to care at all. So there's like a long. Who should I cite? I'm not quite sure. I've never figured that out, but I normally put everybody's name down. But it's a great idea. It's a great idea. And so the question is, could we make it play out sort of along a trajectory? Okay. This is the picture I'd like you to have in your head, right? That if I take my trajectory optimization and I do a time-varying linear controller along the trajectory, right, then I should be able to come up with a region that surrounds that trajectory and will eventually act like a funnel that gets into that space, right? And really, I want you to think of this as a funnel, and I did this, right? I want you to think of that as a funnel that really takes initial conditions, through time along this trajectory and gets you into the space. But let's just think about, how do I write that down, right? Can I use the Lyapunov functions to do that, right? And we can, of course. Okay, so how do I define a funnel along a trajectory? So if you'll remember from the time-varying LQR, this is TV LQR, time-varying LQR, right? That was the case where I had my dynamics where x bar is a time-varying function of x. This can be time-varying too. And the thing I got out of the LQR control design was time-varying controller and my cost to go function, which I could write either in terms of x bar or x, but I'll just. Right? So I remember I have this thing is symmetric and positive definite, semi-definite, I guess, in general. And then this is same for Q, right? Okay, so the story we told for the Lyapunov verification was, one of the stories we told, was that you could potentially use the LQR cost to go as a Lyapunov function, right? So if you wanted to start with a Lyapunov function and verify it, you could use the cost to go function coming out of LQR as my candidate Lyapunov function, and then ask the question for what, that's based on a linearization, what states for the nonlinear system is the LQR cost to go still a Lyapunov function for the nonlinear system, right? So the cost to go is a Lyapunov function. Certainly the time invariant, in the time invariant case, let's just do it one at a time. It's definitely a Lyapunov function for the linear system. Not sure why I'm so pixelated there, but. And locally, it's going to be a Lyapunov function for the nonlinear system. And as long as I have some smoothness properties of my dynamics, then the linearization is valid, at least locally, and the Lyapunov function for the linear system will give me at least a local Lyapunov function for the nonlinear system. And then we did region of attraction estimation to try to figure out where that, where the boundary of that was, right? Right, we would formulate a problem which says, find me the biggest ellipse, for instance, where I could still prove that it's a Lyapunov function for the nonlinear system. Okay, so what are we going to do in this time-varying case? I have to be careful because my nominal trajectory in this time-varying case, it might only be defined for some finite amount of time, right? The duration of my trajectory. So I can't really talk about stability and basins of attraction because all of the definitions of stability and basin of attraction, we're talking about the limiting performance as time goes to infinity. And I'm going to run right off the end of my control tape, right? And I have to somehow be more careful about how I talk about that. But we can still talk about whether instantaneously, if my cost to go function is going downhill, and I can still make statements about, I'm converging to my trajectory for the duration of the time of my trajectory, right? I just can't say I'm going to absolutely converge with this Lyapunov function because I might run out of time. Okay. So what we have to ask for in the time-varying case, unless you define, you could define a trajectory that goes to infinity, but typically in the time-varying case, we ask for some finite time property to hold. Okay, so where before we said this was our statement for regions of attraction, right? I switched too fast on you guys. I just said ask for finite time behavior instead of stability. Here we said, find me, show me that for all j less than some rho, I want j dot to be less than 0. Remember that picture? Right? So I have j is my Lyapunov function. I'm going to say rho is my level set of my Lyapunov function. Right? So this is some and I want the sub-level set to have this property, and then of course j dot at 0 has got to be equal to 0 in a simple case, right? The time varying case, I'll generalize that a little bit. Now I have jx and a function of time, right? Because I've got my time varying cost to go. I'd like to say something like this. For if whenever j is less than some rho, I could pick a constant rho, but in general, it's okay. I can be more expressive with a, well, let's leave that off for a second. Do it first without, okay? I'd like to say that j dot x of t is less than 0, and again, j dot 0 of t will equal 0. So what would that tell me? Now I have some time varying, right? I have some trajectory through time, and at every instant in time I've got some quadratic function sitting on top of it, right? And so I'm going to pick a level set of this and say that I'm always going downhill, but the problem is not the problem, the property is that this bowl is moving through time, right? So if I'm going downhill, but in order for this to be satisfied, I also have to move along with the trajectory, move along with that quadratic function as it moves through time, right? Because remember my function was x bar s of t x bar. So my quadratic function is moving along in time. In order to go downhill like this and get to the trajectory, I have to move along the trajectory. Okay? So that works. That works fine. It turns out we can do a little bit better. Okay? So we can actually say that j dot less than rho of t, and we can make some of the same statements, right? We can make basically all the same statements if I'm less than rho dot of t. This is just a generalization because last time rho dot was 0. So I can say, this is maybe a hard thing to intuit, but as long as my, this defines some now shape along in time of the trajectory, okay? And as long as this property holds, I'm going to stay inside this time-varying region, okay? Because at the boundary, I'm always going to be going downhill. So wherever I look in time, okay, if I have my nominal trajectory, I've got my level set here, around it in time. So this would be, say that's x nominal time. This is the projection down of that level set. This is where j of x t equals rho t, and this also. And it's a moving thing, okay? And what this says is that when I'm at the boundary, or inside the boundary, whenever I'm inside this region, I'd better be going down. If this boundary is if this boundary is getting bigger, that's okay, as long as I stay inside it. This could be, j dot could be positive, but as long as I stay inside this boundary, then this boundary is somehow still meaningful, right? This this time varying region defined by the level set, the time varying level set here of j. Okay. So we can extend the time invariant Lyapunov story nicely to the time variant case and come up with these funnels in state space, right? Using, again, sums of squares optimization. I won't write down the formulation. We've got it, we'll have it in the notes, and it's certainly in some of the papers that are out there, okay? And we can do all the things we wanted to do before. So for instance, even in the time variant case, can do robustness analysis. With common Lyapunov functions. Right? We can search for the largest row for which we can prove this. Although defining largest is not obvious. Not obvious how you want to define volume over the entire trajectory. We can do a lot of these things with sums of squares. Okay, now there's a really important point I want to make. So for this picture that I had, not that picture, this picture, I don't actually need my trajectory to converge. I don't need my system, all these initial conditions to converge to the trajectory in order to make my funnel story happen. All I need is that the final conditions as I exit my trajectory follower end up in the initial conditions of my balancing controller in this case, right? So actually, I don't even strictly need to check that the j dot is going downhill everywhere inside there. All I really need is a statement about invariance. I want to say that none of the trajectories leave the region once they start in the region. And I want to define a region which lands in the funnel I care about, and make sure that no trajectories of the system will ever leave that region. Okay? So that's a simple change here, is I can ask for invariance by just checking the condition when j of x equals rho of t. Okay, so that says when I'm on the boundary for all, if I look at the dynamics of the Lyapunov function on the boundary that I've defined, on the boundary of my funnels, I need that every trajectory that starts in that, every velocity is going into my funnel and not out of my funnel. Okay, I can do that by checking, along the entire trajectory for all time and for all x where I'm at the boundary of my funnel, and making sure that the derivative is pointing in. It's useful to stop and think. I mean, so you could do that. You could try to do that by evaluating numerically at a bunch of points along the trajectory. But you'd never be sure if you missed something, right? So there's something kind of cool about doing this with sums of squares where you actually do it algebraically and get a certificate out that's valid for all x in this place, right? Okay, so what I want you to understand is that the mathematical certificate you get is that if I define the boundary of a funnel, I can use sums of squares to verify that I'll never leave that funnel. Under the open loop dynamics, under the closed loop dynamics, the case I've sort of hinted at here is that you've used TVLQR, so you have a feedback controller trying to stabilize your trajectory, and you're going to say that I want to make sure that the feedback stabilized system stays inside the funnel. There are a couple subtle points that make this work well. Okay, so one of the subtle points is that for any real system, I don't actually have analytical descriptions of the nominal trajectory. Right? If I say I'm going to stabilize a nominal trajectory, I don't have an analytic solution for this nominal trajectory, which is actually exact for the real dynamical system. What I have is a trajectory that came out of trajectory optimization, which is a piecewise cubic, for instance, right? Some spline approximation of a trajectory, and it satisfies the dynamic constraints up to some numerical tolerance, but it's not really a true trajectory of the real system. So if I ask for the system to converge, algebraically to some trajectory which is not even a real trajectory of the system, I'm going to get into numerical issues. I'll be flirting with numerical issues. But asking for invariance is sort of a safer thing. I can still ask, even if it's not even exactly the boundaries of an invariant set, I can still ask for any old circle. I can ask, does the system ever leave that circle, that ellipse, or that time-varying funnel? And that works. That's numerically a reasonable thing to ask. If you care about stability, you can ask for other things. Sometimes we have said, for instance, I want to verify that the system converges, that V dot is negative, between this level set and this level set, but you leave out sort of a little tube around your numerical approximation. You can say, I converge to this inner tube, for instance. That's another thing you can ask for. Okay, but there's some subtle things there. And remember,